plus the opposite, right? And H is a measure for the size of the element, so the average. And we also have the average of the gradient of V, and here we have a penalty parameter alpha, and for these kind of problems, they're stable for any value of alpha which is larger than a threshold value epsilon, and that epsilon can vary depending on the problem you're looking at, the order of your finite element spaces. So we compare that to a GG lifting type formulation, which looks a bit different, and we have these lifting operators, so capital R, and so we have 4 terms here, actually, almost like we had before, plus a stability term. And the thing to notice here is that these methods are stable for any positive value of eta. And the lifting operators are defined such that capital R is just the sum over the facets of this lifting function, and the lifting function is defined as the integral of the test function for this lifting space multiplied by the lifting function, then integrated over sort of a macro element, which is just 2 elements sharing a common edge. So we have the values on one side and the other side, and that should be equal to minus the interior facet integral of the average of the test space multiplied by the jump of the trial space. So how do we implement that currently? So all this is what we currently do and what currently works or appears to be working. Anyway, so we compute here the coefficients of this lifting function. So it's no longer a function, it's you can look at it as nodal values. So we compute that by evaluating this interior facet integral using the average of the lifting space multiplied by the jump of the space that we use for the trial functions, and then we multiply that with the inverse of the mass matrix sort of the lifting space. And all these basis functions are defined on macro elements, so we have still the values on the minus side and the positive side, and we need to take all that into account when we evaluate and dump it into the contributions of the local stiffness matrix. So here we have, to compute the integral of the contribution, we have the derivatives of this test function, and then we have again this lifting space, and we multiply it, we integrate over the macro cell and multiply by these lifting coefficients. Yeah, so that's pretty complicated, but luckily we have some fantastic tools in a FEniCS toolkit for that, so we can actually define some form files for these 3 forms in the following way. So we have the elements for our space, element space for V and U, and we have our lifting space, which is sort of a gradient space. So we have just a scalar element, and we have here a vector element 1 order less, and we then define this bilinear form to evaluate this term here, the mass matrix here for also on the macro element, and then we have a sort of a standard interior facet integral that is already supported. So the key problem is now we have all these simple forms, but everything, as I showed before, was defined in terms of these basis functions that were defined over 2 elements. So we need to evaluate this and construct sort of macro element integrals. And to do that, we implemented these 2 functions in, actually it's the finite element assembler from Dolphin. We just call it the lifting assembler, so it's not in there yet, it's not merged or anything. And this work I did in collaboration with Jay Gaussian. So let me just run through some of the shenanigans for the lifting terms. So first we loop the cells of the mesh, then we loop the local facets on that cell, then we get the associated cells for that facet and compute the lifting coefficients on that macro element. So they're actually macro lifting coefficients, and assemble the macro element tensors for that left-hand side. So finally, when we evaluate the lifting coefficients and this integral here defined on the macro elements, we can then just multiply it to get this contribution to that part of the local element matrix, and then keeping track of the degrees of freedom, we can then map it into, yes, honestly.
Did you use these forms, but just locally? Is that, did you use the forms that you showed on the previous slide?
Yes, that's locally, so we just take for this could be the minus element, and then this would be the plus element.
And that's the mesh that you can do now. The mesh is...
Yes. So I sort of just take the two elements at a time, compute sort of the macro element contributions, multiply it to, and there you have it. And then for the capital RR term, it gets a bit more involved. So then we take another loop, so still within this first loop, of the local facets, again get the cells, compute the coefficients, evaluate this here integral, and then we just multiply it like this. And the stabilization term goes in much the same way. So it looks a bit expensive, and it is. This is sort of the element patch. So for the involved degrees of freedom, so it's like a sparsity pattern. It will look something like this for this kind of formulations, compared to the IP method, which is already bad and slow compared to just the standard CG, where it looks like this. So it will be a bit slower. But let's look at a benchmark problem. So if we have the Poisson equation with this source term on this domain, and we have this exact solution, we then have for compare three different formulations. So continuous Lagrange using linear elements, and discontinuous IP formulations, so discontinuous linear elements, and GG lifting formulations. So linear discontinuous elements for V and U, and then constant lifting space, and we see we get a K+1 order convergence, which is quite nice. And then we see what happens when we do constant elements for the IP formulation and the lifting formulation. So in this case, for the lifting formulation, we use constants for both V and U and also the lifting spaces. And we see we still get K+1 order convergence for the lifting formulation, but for the IP we get I don't know, constant convergence, is there a thing like that? I don't know. 0th order. Okay, so anyway, let's just look at the solutions on an unstructured mesh. So we have here, which is the lifting formulation, the solution for that, which I personally prefer, but we learned today from class that I cannot criticize this solution in any way. Okay. Anyway, so there is a difference, definitely. So the motivation for it, so why we ventured in this in the first place, is that for gradient plasticity, the yield function could potentially involve a term like this, so the Laplacian of kappa. And if we want to use discontinuous constants to solve this problem, then as you saw before, this solution might be wrong if we just use an IP method, but with using the lifting type formulations, we can sort of compute still correct results, or more correct results. So this is future work, perhaps, I don't know, because as I said, it was quite complicated to come up with this, keep track of all the different small forms and the Duff maps and all that. So maybe if we could define this in UFL, so I guess you still have a couple of weeks left, Martin, so please. So if we could define something like this, right, a null space, a lifting space, and just a lifting function or operator, whatever, and then maybe define a new kind of integral that will, I guess, create some new functions in UFC, where we send in 2 elements or even more, or something like that, to compute to compute the contributions of these, of for instance this term that looks like this, so the VR term or the R term or whatever. So I don't know, it's something to consider anyway, and we're thinking if this might be possible. I don't know how to do it, that's why I'm sort of throwing this out in the open, so we have a common ground for future discussion. Anyway, I think that was just the summary. Yeah, it has some attractive properties. The implementation is more involved. Yeah, and it would be nice if we could automate this even more than it already is. I mean, I do build it from these minor parts of FFC and construct sort of something that works, but if we can do it even more automated, it would be nice. Okay, thank you very much for your attention.